information on IUPAC in here. So there's a couple things that we could go through and fix. For instance, these boxes are weird. That's just a font issue within the system. What those are supposed to be are arrows. So you're responsible for being able to know your number of carbons, primarily up to 6, but ideally up to 10. You should know your functional groups. Okay, so one thing that doesn't show up on this slide is that you're responsible for knowing what an alcohol is. So you should be able to look at a structure and be like, bang, that's an alcohol. Because once you know it's there, then you can name it. If you don't know what it is, then you can't name it. So there's some kind of pre-existing knowledge that goes with this. Okay. After that, it's now kind of processing through all the rest of the information. Okay, this first red box, the functional groups are named by suffix, listed first if they are highest priority. Okay, so what that means is the first name in each of these would be the highest priority. So if we're saying that structure has the highest priority functional group of an alkyne, the ending of the name is YNE. How do we know it's an ending? That ending is because of that dash. Okay, the dash that kind of leads out in front. Okay, if another group of higher priority is present, then the lower group gets the secondary naming rule. The secondary naming rule is what's following each of those arrows. So these are all secondary naming rules. Okay, and you'll see that they have a dash on either side because that functional group is now getting placed into a different location. That name gets placed in a different space. Okay. The next box is that blue box, and this summarizes the primary systems that you would go through when assembling the name. So you need the longest carbon chain. That contains the highest priority functional group, and that becomes one of the big ones as everybody goes, oh, here's the longest carbon chain. There's no up, down, left, or right. It's very easy to draw a long carbon chain that doesn't contain the highest priority functional groups. So you have to make sure that your longest carbon chain contains your highest priority. Then you identify your highest priority functional group and the substituents, define the location for each, and then you start kind of putting the structure together. After that, there's tons of rules. Okay? It's literally a textbook worth of rules in nomenclature. So the hope is that I've carefully selected and curated nomenclature questions that follow this system and don't go beyond it. That doesn't mean I'm perfect, okay, but that's the intent. Kind of makes sense? Okay. All of it requires application, so you would need to push out to some practice. The best place to find practice is on the internet. Try to assemble the name according to these rules and then compare back to what the answer is according to the internet. Okay. You will find undoubtedly that there are names that don't align perfectly, okay, and you might be a little bit off. Defining what a little bit is going to come down to, should I have known that rule or that part that allows me to see that? That does become a little bit more challenging to nuance, but that becomes kind of the challenge that we have to deal with within the class. What did I want? I want to get rid of this and then close this. Really? That's... Let's see if we can find...
65.
Holy crap. Did you say 65? Oh my god. It's totally not going to load that. Please load. Oh, maybe it will.
This is going to be like a good...
Okay, there we go. We actually get a couple names.
Of how the finals kind of look. 70 questions, right?
I think we're going to sit at 65, assuming that's okay with you.
Yeah.
Okay. Mostly because the time that I thought I had to write the exam, I've been filling with a bunch of other work, so I haven't been able to get to writing more questions. So we've got 2 IUPAC questions here, and we could take a look at both of these. Okay. First and foremost, when you go through and take an exam, any exam, theoretically, most questions within the exam, particularly for a multiple choice, you should be able to answer them without looking at the answer choices. So your first approach should be, I'm not going to look at the answer choices and I'm going to write down the answer. That should be your first approach. Okay? If you look at it and be like, well, I don't know what the answer is, don't look at the answer choices. Move on. Okay? Because you already have established that you don't know what's happening within that question. More than likely you're going to get it wrong. Move on to a different part of the exam. Maybe you'll get that question right. And if you spend your time passing through those answer choices, you're wasting time that you could have spent increasing point values elsewhere. Does that make sense? And the last piece I'll point out is that if an exam is well written, all of the answer choices can be explained. Every single one of them. Okay? Which means if you don't know the content, you can convince yourself that the wrong answer is right. That's a problem. Okay? So if you're stuck and have no clue what's going on, it is fine to go into the answer choices. That's called test-taking strategy. You're okay to do that. Just realize you should be doing that after you've proven your content knowledge everywhere else. Okay? So step 1, we'll erase the answer choices and we'll see what we can come up with a name. My strategy, particularly if you have different colors, okay, would be to highlight the main chain. The main chain might run left to right. It might run top to bottom. It might run top to right. Okay, so you've got to establish where that main chain is. So we could go through and identify our longest carbon chain. Conveniently, there are no other carbons, so it's going to run a straight chain like this. Okay. The next part is we have to ensure that it has included the highest priority functional group. Okay, so what functional groups are present? There's technically 2 within this structure. And what I would do is actually highlight like this, highlighting the main chain. What are the 2 functional groups that are present? There's the alkene. The other one gets a little bit weird, so I don't blame you if you're struggling with naming that one. You could call this a bromo or a halo. Halo is the class, right? Your halide or your alkyl halides. We're getting more specific because we know it's bromine, so we could call it bromo. We don't want to call it bromide because bromide implies that it's sitting on its own away from the structure. Okay? That already gets us some information that we could, if we had nothing else, we could go into our answer choices. Okay, again, we've got more skills than that, so we're going to try and push on it a little bit further. Okay, the alkene, being the higher priority functional group, is going to dictate the end. Since I've memorized what my functional groups are and the names, that already gives me a tip-off to what the end of this name needs to be. I'm going to see ene in the end of this name. Okay. I also need to specify where that alkene is in the main chain. Because it's the highest priority, I want to assign it the lowest possible number I can. Okay. Again, I've highlighted the main chain. Should I be numbering left to right or right to left? What's going to assign a lower number to my alkene? You said so many rights and lefts in there, I have no idea what you're trying to say. So try again.
If you count it from left to right, it has a lower.
And I fully understand. I'm getting lefts and rights confused easily. Like I could probably screw it up too. So 1, 2, 3, 4, 5. So where did the alkene show up? Position 2. Okay. That also gives us information about the bromo. We know the bromo now shows up at position 4. Right? If we're now going to provide more context behind this and start to assemble our name, our longest carbon chain is 5 carbons. 5 carbons is known as pent. So that's that kind of root aspect of it. Okay. What's the highest priority functional group within it? the alkene, that modifies the ending of my name with an "ene," and I can specify the location of that "ene" in front of it. That locator number, unfortunately, can jump around. Okay? It should be as close to the functional group as possible, but you will sometimes see it jump to in front of the pent because there's no other functional group with which that two could be confused. Does that kind of make sense? So IUPAC says certain rules. The two has to be immediately, the locator has to be immediately next to the functional group. Okay? That's not always done correctly. I try my best, but IUPAC is definitely a weakness of mine. So we know our root structure is going to be called pent2-ene. We have identified the main chain, we've identified the main functional group and its locator. We now need to include the final substituent. Where's the final substituent? That was 4-bromo. Okay, so put together we have 4-bromo pent2-ene. The last thing that we could look at would be, do we need extra information about anything within this? Okay, at that point, what I would do, okay, because it's easy for me to go through and do it, less easy for y'all to go through and do it, would be to actually look at the rest of the structure and be like, is there more stuff I could label? Which is kind of a hard question.
Because wouldn't that be like, say you had like 2 bromos? Is what you want to go like?
I don't know what you mean by 2 bromos. You can keep talking.
Like what was the, where you would do like 4, 4 versus
So you could say
4,
4, dibromo, because
Yeah.
we have multiple bromines. So you get a locator for every single substituent. In this case, we only have 1 bromine. We don't need a dibromo. We don't need to do the 4, 4.
And you would you do both 4, 4 and di?
Yes.
Okay.
Anybody else see anything potentially suspicious about this structure?
You don't have to say anything about it being wedged, do you?
So yes and no. Okay, at this point, because we don't know what the answer choices are, because we've decided not to look at it, is that a chiral atom?
Yes.
Yeah, which means, should you specify it? Yeah. Okay, this is where I would argue you could quote unquote cheat and be like, do I really have to spend the time to do RNS? Okay, how would I decide whether I really had to do the time to spend the time to do RNS?
If you looked at the answers and it was part of the choices, yeah.
And that tells me right away, yeah, I need to worry about RNS. Okay, it should also tip me off to something else. I also have to worry about the double bond and the alignment of the substituents around the double bond. Okay, you immediately jumped on the cis-trans, so it sounds like you understand that better. So walk me through how you've decided that this is trans.
Oh, I just was saying that was another thing that we'd have to figure out, I guess, with the E and Z. But we would have to do,
So I believe what you're saying for the sake of the recording
yeah,
is that you see E and Z's, which you know is referencing cis and trans, which means not only do we have to do RNS, we also have to do E and Z.
yes.
Good. Okay. So then we'll switch it up as a slightly different, I wasn't supposed to delete all that. We'll switch it up to a different question. Is there something, and you've asked this question, you started us on this track, so we'll leave you to guide us. Do you find cis and trans or E and Z easier or RNS easier?
I would say cis and trans easier, but I
Okay.
am not sure where I should essentially
So if we walk through the process, okay, what I've suggested is you cut it in half perpendicular to the pi bond, and you look at each half. Okay? When you look at each half, we have to be careful about something. What we have to be careful of is that there's implied atoms. There's an implied hydrogen here, and there's an implied hydrogen here. And what we're now going to do is compare that blue dot to that hydrogen and decide which one is higher in priority.
The blue dot.
The blue dot. What's the blue dot?
Carbon.
Carbon. Why is carbon higher in priority than hydrogen?
It's more no, it's bigger.
Bigger is typically in reference to the number of electrons, in which case, no. We run into weird phrases with bigger. So, like, let's try it this way. Is everybody somewhat familiar with sports? Okay. Basketball, the center. Person playing center in basketball, are they big? Okay. How about in football, the person snapping the football back to the quarterback? Are they big? So does that mean the person snapping the football in football can play center in basketball? Ooh, no, they can't. Why not? It's not even just different skills. It's different bigs.
Oh, because he's big, like tall?
The center is typically very tall, and by being tall, they do pick up some muscle size. But if you compare them to the center in football, that guy is big around as well as muscle size, okay? But the height is less of a component of what he needs to go through and do. Or I guess she as well, depending on which sport you're in. It's going to be similar systems. Okay, kind of makes sense? So big has vague meaning. Are you talking about height or are you talking about mass? When we talk about it with electron or with atoms, are we talking about the size of the atom, how big it is, radius, or are you talking about how massive it is? Because those are two very different things. The size radius is dependent on the electrons, and the size mass is dependent on
It's mass, it's weight.
what dictates the mass or weight.
It's number on the periodic table that gives the mass, the molar mass.
That's again a number, but what dictates that number? What controls that number?
It's
What has mass in an atom?
neutrons and
Protons and neutrons. So if you're saying big because the number of electrons, nope, irrelevant. Okay. Priority, when we look at these nomenclature systems, is based off of atomic mass. Not the radius, not electronegativity, not any of those other trends. It's based solely off of atomic mass. Okay? And I want to be clear on atomic mass. Okay? When we go through to compare the blue dot to that hydrogen, it's carbon to hydrogen. Even though, if we listened it probably didn't get picked up in the video, someone said CH3 to hydrogen. No, it's not CH3, it's carbon to hydrogen. Because I don't care what the other atoms are that are connected. I only care about the immediate atom. Does that make sense?
well, you just said what is the blue dot?
I know, I left it intentionally vague. Right? And that blue dot is specifically the carbon. The things connected to it will be ancillary to it. So in this comparison, what do? We would go through and star the highest priority. And we move to the other half of our molecule and we do the same thing. Which is higher priority, hydrogen or the green dot?
The green dot, because that carbon's connected to the bromine? Or
Don't care about the bromine. What is the atom at the green dot? Carbon. And what am I comparing it to?
Carbon. Oh, that hydrogen.
I'm only looking at half of the molecule. That's the point of the red line. I only look at one side of that red line. And I compare the pieces, the bonds coming from that side. So I'm comparing carbon to hydrogen. Carbon has a higher atomic mass. So the carbon up there should be starred. Yes, bromine has a higher atomic mass. I don't care. It's not the atom connected. When would I care about moving further out? If there's no difference between those atoms. If I can't see a difference, then I move out to the next highest priority atom. Okay? So it's only when there's no difference do I have to navigate further out. Okay? Now that I've got my stars, I can now slice parallel to the pi bond, and I say, where are the stars? Are they on the same side or opposite sides of that line? They're on opposite sides, which means trans, which means E. Okay. The only way I remember it is cis is the same side, which is stupid, but even when I get trans, I will still go through and say the same side to try and make sure, oh, it's not that one. Okay, so it's got to be whatever the other one was. Okay, so I answer it by looking at the negatives and saying, well, those aren't right because they're z's. Okay. We also said we had to address the RNS, the chiral atom. Yay, we get to do the whole process again, except with a little bit more complexity, because in that little bit more complexity, we also have to remember there's an implied hydrogen. And we would now go through and do a somewhat similar system, but our focus is now at that green dot. Okay, and I guess we should say the trans E. So we go through and we assign priorities, similar as to what we did for the pi bond, but now we just focus on the atoms. So bromine, having the largest atomic mass, so it gets assigned a 1. The hydrogen will have the lowest atomic mass, so it gets assigned a 4. I would then look at the other atoms, and I'm looking at carbon versus carbon. Is there a difference in atomic mass?
Not carbon versus carbon.
Not carbon versus carbon. So what do?
What it's connected to.
I move one atom further away, I encounter a hydrogen, whereas in the other case I encounter a carbon. Carbon has a higher atomic mass than hydrogen, which means this carbon gets a 2, this one gets a 3. Now that I have my priorities assigned, I have to ensure that I'm looking at the molecule from the correct orientation. The hydrogen must be aimed away from me, the lowest priority must be aimed away from me, which is typically hydrogen. It is aimed away from me here. I can now go through and I can connect the dots 1 to 2, 2 to 3. Okay, which direction would I be turning?
Counter.
That would be counterclockwise, and I screw it up all the time too. Counterclockwise is assigned S. Okay? Officially, we should be extra clear. The S is being assigned to which carbon? Since we erased everything, now it's really confusing to backtrack where it all came from.
The second carbon. Is that determines the direction you're going?
It's not the second carbon.
Oh,
It's
yeah.
the fourth carbon. So I should be saying 4s. At position 4, it has an S chirality.
Because it'll always be your chiral atom, right?
When you see S, it's going to be chiral. If there's only one chiral atom, that's why you typically don't have to include the number, because there's only one.
Yeah.
You can't get confused. Okay? Again, IUPAC says you must be explicit. Okay? Where is the trans?
Is it one?
Is it at the first carbon? Do you have the alkene there? Do you have the alkene starting at carbon number 2? Yeah. So this should be 2E, 4S, 4-bromo, pent 2-ene. And now we've assembled, officially this gets parentheses, and then I think it gets a dash, but I could be wrong on that. We need a comma in there to separate those. And we would have our full formal name. Kinda, sorta? That's lots of intricate pieces that go into this process. You're responsible for all of those. Will you be tested on all of those? I can't answer that question. I'm sorry.
What
but
is the 2 assigned to trans?
So
Because we didn't compare that. That's where you drew your first line.
So the trans is in reference to the double bond. Where does the double bond appear in the structure?
Oh, okay.
It appears at structure or carbon 2.
So say that was a cis structure, it would still be 2.
It would still be 2, and we would just switch it to 2Z. Kinda, sorta?
So with the multiple, like, choice answers, I know you said you wanted to figure this out before you're looking at that, it would be, like, what would we select, I guess, if you erase the work?
Yeah, I want to get the name in here so we have it to look at. And this is one of the reasons why I dislike nomenclature with a passion, is that nobody follows the frickin' rules.
Yeah, 'cause, yeah.
So we can immediately look through and we can see that I already screwed something up. Okay, what did I screw up? The order of the E and the S. S or R is supposed to go first, then followed by Z. Why? Because there's a rule. There's a rule that says it, so I'm wrong. Okay? I don't know that rule because I'm an idiot. Okay, we can establish that. Okay? But since I know how to name it from a multiple choice standpoint, I can quickly go through and say, well, it isn't R, so those are wrong. So I'm looking at A or B. Within A and B, I know it was an E configuration. Oh, so it's A. Okay. Did I need to know it was 4-bromo pent 2-ene? Not really. I mean, kinda. Okay. 4 answers had that exact same root structure. So if you knew that root structure, you could eliminate answer choice E, but that's all you would be able to do. So really, what was this question asking about?
Cis and trans and
Yes. The question was asking about cis and trans and RS. It really didn't care about the rest of the nomenclature system. It just cared about how do you assign cis and trans and RS. Kind of, sort of?
Can we do one more of the IUPAC?
One right underneath it.
Wait, no, can we do, not that one? Can we do 17 from exam 3, I think?
Are we okay with that? Should I quickly do this one, or is everybody okay just skipping this one? Skip it? Okay.
Do you want this?
Oh, yeah, because I don't have copies readily available.
I think, so I got it wrong, but I think the answer is A,
This is one I would have liked to have done. I was hoping it was actually in this.
but I'm very confused. 'Cause I felt pretty confident that I had it.
And this one, let's see, how do I do this? I want to do my picture here. $17. Okay, I did kind of screw up because I should have done a white background. Okay. So this is, again, where I would process the rule sets that we just had up on the screen. Okay, so first we should get rid of those. Okay, because again, if the answer choices were well written, if the answer choices were well written, every single one of them has some bearing in truth behind a student misconception. Okay, so step one, what do we need to do?
Count your carbon chain.
So we got to be careful, because step one does say count your longest carbon chain, but it says something else. That contains the highest priority functional group. Right? Most students swing at this one and go, here's my longest carbon chain because it contains
It's the most amount of carbon.
the most amount of carbons. Does it contain the highest priority functional group?
No.
It does not. Because it does not, that is the wrong chain. That answer choice shows up there.
So how would you count it, including the
6.
ethyl?
Okay? So we know the alkene is our highest priority functional group, so it must be included in our carbon chain. Okay? Because it's included in the carbon chain, we have to be including out here, and so we're going to circle down and now decide where do we go from this branch. Do I go to the left or do I go to the right?
You're smack dab in the middle. But you
Six.
have
Thanks, I just needed to count that out. And if we go through and look at that, we are smack dab in the middle. We get 6 carbons regardless of which way we go. Okay, so what I'm going to attempt to do here is do both.
But when do you go the other way? Because it's so.
Oops. We kind of get what I'm doing here, so we'll do 2 different names. We've got an orange name. It's 6 carbons, regardless of which way we go. So we've got, what's our root?
Hex.
Hex. Okay, if we were going to number, we need to number with the lowest number assigned to our highest priority functional group. Our highest priority functional group is the
Alkene.
alkene. Okay, so I want to go through and assign the alkene what number?
1.
2, because there's an extra carbon out there. 1, 2, 3, and then it splits either direction. So our alkene is at position 2. Ene, if we went the red path, it's still 6 carbons. I'm going to shift that over a little bit just in case I need it. Okay, and then I would have to go through and process kind of the rest of this. I wanted to do this all in one structure. I can't get away with it. So we'll call this one our orange one. Oops, man, I didn't want to erase that. And then our red one, I'll draw next to it. 2, 3. Hopefully not changing the name at all. Okay. So if we then move on to identifying our substituents, in the orange one, we've got 2 substituents. Circled that one a little bit off. Okay, what are the 2 substituents we've got? Well, I circled a 1 carbon, which means I have a,
Ethyl.
sorry again, say again, a methyl. And I have a 1, 2, 3 carbon, which is a propyl. I need to specify the locations of those. 3, 4, 5, 6. At position 3, I have the propyl. At position 5, I have the methyl. Does this have cis-trans isomerism? Yeah, it does. I don't think this question is asking about that. We'll see that in a second. Okay, but I'll try and overlay that. How do I do this without making it? It's going to look like a mess. No 2 ways around it. That carbon is higher priority than the hydrogen. If we look at the other half of our structure, this carbon is going to be a higher priority than the other carbon because it has an extra carbon on it. So you can go through stepwise to prove that to yourself, but you're going to end up comparing carbon versus hydrogen. Your star is going to be there. We cut it in half the other direction. Where are the stars?
Different size.
Different size, which means trans, Z, so E. And officially it started at 2, so I'd have a 2E structure. You'll note that when you look at my work, have I put that together into a name?
Not yet.
No, I haven't. Okay, and even with the other one, I tried to avoid putting it into a name as much as possible because that requires an extra rule, and that's alphabet and all that, and I'm as bad as at the alphabet as I am with R and S, with left, rights, and all that stuff. So what I'm hoping is that I have enough information there that I can whittle down what my potential answer would be. If we move to the red one, circling our main chain is out there. So we have one substituent because everything else is identified. What is our one substituent? Well, it has 1, 2, 3 carbons. So it has a 3-carbon chain, so it would call it a propyl. But that 3-carbon chain has another substituent on it. So I would call this a methyl propyl. Where's the methyl located? It's located at position 2 on my propyl, so I would call that a 2-methyl propyl. Does that suck? Yes. Absolutely. Okay, but that's the rules for that nomenclature system. Okay, I then have to specify where the propyl is located on the hex 2-ene. That's dealing with my 1, 2, it's at position 3, so I would get a 3 2-methyl propyl, hex 2-ene. Okay, the double bond is still trans, so I would still call that 2E. Right? Between those two names, which one do you like more? And you could be like, I have no preference.
This one just because it's less messy.
Okay? I would argue yes.
Or
I completely agree with you.
there's no.
There's these pieces, there's no this weird funky chain system. Well, you can get weird funky chain systems. That absolutely does happen. But when we go through and try and do nomenclature, we want to limit the weird funky chains because we don't want to have to deal with that extra nomenclature system. Okay? And what that boils down to is a rule that your longest carbon chain, when there's a tie, so we had a tie, 6 carbons, orange versus red, that we pick the chain that produces the most substituents. So the orange one has 2 substituents, the red one has 1. Does that make sense? Is that a gross rule? Yeah. It is. Right? And if we go through and look at our choices, what do we have? Okay, I see a 4-ethyl, I said it was 5-methyl, so A can't be right. I said 5-methyl, yep. I said 3-propyl, I said hex 2-ene. It doesn't say anything about E or Z, so I might be like B does not look like a good answer because it doesn't say E. But if I look at my other answer choices, does it say anything about E? Mm-hmm. No, so I don't have to worry about it. Okay? So B looks good. It matches the orange split. Okay? What happens when I move to C? What the hell is ISO? And if you're like, I don't know what ISO is, that's good. It's not IUPAC. Okay? It's a common name. What's the name for H2O?
Water.
It's dihydrogen monoxide.
Oh.
Why do we call it water? It's a common name. So when naming organic molecules first came about, they came up with weird naming systems. They then ultimately decided that those were stupid naming systems to have, and they switched out. Okay? So you don't know what that ISO term means, which is fine, which ultimately means
It's not the
It's not iso. Okay? We can then move to the other one, 4-ethynyl 2-methyl-hept-4-ene. What is an ethynyl?
No idea. I thought that just said ethyl.
Which is the other frustrating thing within nomenclature, because one letter can change the entire meaning of the whole system. Kind of makes sense?
Yeah.
So within that, and this, it broke down exactly how I wanted it, but I didn't want to say it before I erased the answer choices. Okay? Only one path leads you to the correct answer, which is why I didn't provide 3,2-methylpropyl, because that's now pushing into a rule set that we didn't talk about. I'm not trying to make you try and memorize rules that we didn't talk about. So if you aren't seeing that answer, or the answer that you've come up with, what does that likely mean?
You're not doing it right.
You did something wrong in your nomenclature system. What does that mean? You're now on the test.
Good, try something else.
Move on.
So try something else is a little bit vague for me. Move on is more precise. Okay? Because try something else could mean I'm moving on to the next question. You've wasted a time already on this question. Okay? You're doing something wrong. You don't know what you did wrong. At this point, you've already lost time. Move on to something else. Okay? Come back to it later if you've got time. If you've written down work, you can try and look at your work and hope you see something. So, for instance, hex 2-ene was consistent either way we went at this. Hept, there's that one letter. That's not one letter. Close enough. Okay? Hept is wrong. That's wrong. Hept is wrong. That's wrong. You're now down to a 50-50.
That's if you did it right, though.
And
that's what you start off with.
that's not if you did it perfectly right, because perfectly right means you recognize that your branch has to go
Yeah.
to the left. But if you branch to the right, you still have hex 2-ene.
Yeah, but if you just didn't
So
do
if
it,
you knew none of the content, you're right. The hept makes sense, because the hept is now 1, 2, 3, 4, 5, 6, 7. Are you responsible for knowing that you must include the longest carbon chain that contains the highest priority functional group?
Yeah.
Yeah, you deserve to get the question wrong. Sorry, but you do.
Yeah, I just forgot that part of it.
Yep.
So
Which is incredibly easy to do. Okay? Kind of, sort of? Does that help clarify your point?
yeah.
Do you want to go back to the one that we didn't talk about, or you think you're good now with nomenclature? Okay. So before I entirely box it out, I would highly encourage you to go back to Unit 1 with the nomenclature slides and make sure you've got this reviewed. Okay? Theoretically, at this point, you're probably good with this. Okay, so you could mostly ignore that. Okay, we haven't talked a lot about cyclos, so you could probably get rid of that. Knowing your functional groups here, that's probably more what are your functional groups look like. So that's going back to the functional group list and saying these are what those structures look like so you can acknowledge them.
Which is also beneficial because there's a lot of other questions that will just use the names and not like have the whole structure out and ask questions about it. So you have to know what it looks like.
I'm going to come back to that in a second. That upper right-hand corner was how to use the red box, so we could ignore that. So theoretically, at this point, what you need to do is work on this blue box and make sure you understand the rules outlined within that blue box. You do have to trust me a little bit that I'm not going to throw things at you that require nuanced rules. Okay? They could still require a nuanced rule, but I wouldn't provide both answer choices. I would only provide one that would lead you to a correct answer. Does that make sense? So if you're struggling with nomenclature, I would say that red box and that blue box are pretty critical. Sydney, you said something? God damn it.
So the You said it's good to know what those are, like what they look like, the functional groups. And there's questions on that practice
Oh,
packet
thank you.
that just
That's what
use
I
the
wanted.
name. So if you
Yes.
don't know what it looks like, then you're not gonna be able to even
Yes.
attempt to answer it.
And so, I don't know that I'm able to quickly find something like that. But if you go through and look at some of the questions,
I think they were up in the lower numbers.
I'm not sure I can find one very quickly. So first and foremost, how much does your instructor like nomenclature? Did you say a lot?
Not a lot.
Okay, I was like, what? I thought it came out a little clearer than that. I dislike it so much that when I go through and look at questions and when I edit questions, I try to ensure that I give you the name and I give you the structure. So that if you don't know the name, you could still answer the question because you have the structure provided to you to work from. There are cases that I miss that. When it comes to the practice was built very, 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 very fast. I don't get the time to be able to process each and every single one of those. I try when I select the questions to be like, ooh, that's a problem. I don't want to ask that question because it's going to cause issues like that. But I do try to be cognizant of that and make sure that if I'm going to do a question like that where I give the name, it's a name that I think you should be able to solve.
Yeah.
Not a wild, like, what the hell is this? Okay, you have the structure to work, which might be.
Or like that one where it was like identify them. There's
Yeah.
a couple in there that you said we didn't. Like the answer was it
Oh.
amide?
So this one was amine phenol ketone alcohol.
Was it?
Yes, this one is that. There are other functional groups in this that you're not responsible for. Where did it go? Amide?
Yeah.
The amide is not a functional group that you're officially responsible for. That, I would argue, is a problem. You should be responsible for that. But I screwed that up. That's one that I'm trying to be very careful about. And I think the same for the ester. I'm a little on the fence with the ester on whether that was one you were responsible for or not.
I think it was just.
So the ether, I'm pretty sure, is on the list.
It is.
But the amide and the ester, I think, are questionable. The phenol, I'm pretty sure, is on the list. And yeah, those are things that I try to watch out for on what I told you to do versus what I ask. And I try to make sure they're aligned. So this could be a question. If we were just given the text, what are the functional groups in this? I wouldn't expect you to do that. Because I don't expect you from that name to be able to know what the structure was. Like, that wouldn't make sense. Does that
Yeah.
kind of get that? So if you're given names that are weird, I'll try to also supply that structure to ensure that you can be on the same wavelength. Okay? And during the test, if you're like, I think you screwed this up, I want the structure for this, raise your hand, ask, I'll look at it. And if you're asking about it, it is quite possible that you are correct and I just missed something. Other questions?
I have some that aren't on this
Where are they?
from exam 3 again.
Caveats within this. Number one, what you're asking about is how it's graded, which I would argue isn't particularly useful for exam studying. Okay, because you're going to be in multiple choice, not show your work.
Oh.
So you don't have to stress about how things are going to be graded. It's either right or it's wrong.
I still think if you want to erase the products, this would be a good one to like, what are the products?
Ish. And so that's going to be the next part behind this. Or two parts. Number one, absolutely review exam 1, 2, and 3. You have those. Review them. Figure out why you got the questions wrong. I am verbatim taking off of the test. I've already forgotten the number, but I think it's 20 questions from exam 1, 2, and 3.
20 each or 20 total?
20 total. Verbatim off of the exams. Okay? So if you understand what all of the answers are on those tests, you've got 20 questions right now. Okay? Out of now 65, because I'm too lazy to figure out another 5 questions. Okay? If you know all those other questions, I haven't said that, let's put it this way. I need roughly 15 questions per unit. Okay? If I'm taking 20 questions from those first 3, ballpark math, let's just say it's 5 questions verbatim. I still need 10 more. Where's the easiest place for me to find 10 more questions?
The practices?
The practices, I would argue there's an easier place. The exams themselves, they just won't be verbatim questions. There'll be alterations of those questions. Okay? So if you go through and review those exams, you're looking at 15 times 3, 45? 45 questions out of 65 that you now should be really, really, really confident about because you've gone through and reviewed everything within those tests. Okay? Other easy sources is absolutely the practice. Okay? But the practice sets are significantly larger than those 3 exams. So I would argue it's easier to go through the exams than it is the practice sets. Okay? But that's varying opinions. Okay? Make sense?
I just like the exams because it's also like not crazy answers.
Yeah. Which is another good point. The exams have already been vetted.
Yeah.
Okay? Whereas the practice sets are not as carefully vetted. Okay? And sometimes I don't like how they're formatted, and I would change the formatting and the wording to make them better. So going through the practice exams is yet another reason that you should be focusing on those to ensure that you've got those right. Okay? Back to this question. So I'm trying to read question and okay. I can see some clarity things that I can talk to you about later behind this. So would this be one that I would put on the exam and say, what's the product? I would say no, I wouldn't, okay? For the primary reason being that if I put both of these answer choices on the exam, which one do you pick? Both of them conform. Why is product A favored over product B? There's a bunch of extra information that's hidden behind this that you aren't aware of because I can change the conditions to force one product over the other. Right? So it's not a question that I would ask on the exam, okay, by providing both of those answer choices. I could go through and say, give that product, and then I'm going to quickly just kind of BS something here. Do something like that. Okay. Now, which of these answer choices makes the most sense? So it's asking you to push kind of into what chemistry you would expect for each of these. Kind of makes sense? Okay. For both of these products, what chemistry was I trying to do?
Like a substitution?
It's not a substitution.
Oh, addition.
It's an addition because I lost the pi bond. Okay? If I was going to run the addition, what we're looking at is the starting structure and being like there's two places of reactivity. I have the pi bond and I have the alkyl halide for two sites of reactivity. The pi bond acts as what? Well, how does an alkene react? This has now been reiterated in every one of our last 3 lectures. The pi bond is reactive because it has p orbital electrons. The p orbital electrons are higher in energy than the sigma orbital electrons, so we're looking at those pi electrons reacting. Because there's no polarity associated with it, the electrons must first react, which means this is an electron donor, which means it would act as a nucleophile or a base. It acts primarily as a nucleophile because to act as a base, it would need to react with a strong acid. Alkenes are not particularly reactive in and of themselves. We need something to force them to go through and react. Why does that become important? Well, it becomes important if I go through and I look at the other starting material I'm given. And that other starting material really only supplies lone pair electrons on the oxygen, which would mean it would act as a nucleophile or a base. I do have the hydrogen that is partially positive, okay? So that could act potentially as an acid if mixed with a strong base. Alkenes are not strong bases. So what does that mean? The base thing is off the table. Would I expect the nucleophile to react with a nucleophile? No, that's 2 electron sources reacting with each other, which means the alkene does not react. That's following the chemistry of everything that we've been discussing throughout the semester. Okay? So instead, what I would expect to have happen is the lone pair on the oxygen should act as a nucleophile, which means it needs to react with an electrophile, whereas the electrophile, bromine being a great leaving group, would make that carbon partially positive, and we now have a system that could work. So I want the oxygen to donate electrons, potentially with that partial positive. Okay? How should that substitution reaction now occur? So now it's acknowledging, do I know there's differences in substitution mechanisms? Well, there's an SN1 versus an SN2. What mechanism should I undergo, SN1 or SN2? To answer that question, I would look at the strength of the nucleophile. The nucleophile is not charged, which means it's a weak nucleophile. Weak nucleophiles favor SN1 type. Okay, I could also look at the substrate, because that information is also given to me, and where the alkyl halide is located at a tertiary carbon. Tertiary carbons favor SN1. I have 2 pieces of information, and both of those pieces of information tell me I should undergo an SN1 mechanism, so let's draw an SN1 mechanism. First thing that will happen is the bromide leaves, leaving behind a carbocation. That carbocation could easily go through and react with the lone pair electrons on my methanol. That would produce, or get darn close to producing, one of my products. The oxygen would be positively charged, does not want to be positive, so it would donate a hydrogen, and that would get us one of our products. That double bond is bothering me a little bit. And that's how product B is formed. The other part that we would acknowledge is that this structure has the capacity for resonance. Okay? That capacity for resonance shifts the positive charge to a different spot. Now my oxygen can come in and attack there. Okay? Again, doesn't want to be positive, donate the electrons, and we would get product A. Kind of, sort of?
Is that super important, the hydrogen leaving after it attaches?
So language doesn't leave. We could say it was removed or it was
Yeah.
lost,
Oxygen takes the,
but oxygen takes the electrons away from the hydrogen. So if we're asked to draw out the mechanism, yeah, that's kind of important. In this question, we aren't asked to provide a mechanism, okay? But it does say provide an explanation for how product A was formed. Well, how was it formed? We have resonance. So yes, resonance is critical to how product A was formed. Why is the product A the preferred product, which is why it was circled. Because if we're going to say resonance, and I go back and I look at this blue structure versus the orange structure, the blue structure is a tertiary carbocation versus a secondary carbocation. Which carbocation is more stable?
the tertiary,
The tertiary, which would suggest what product do I get?
that product.
Product B. And yet the question says product A is preferred. Why is product A preferred? So resonance really just addresses the how. Why is product A better than product B? What is the difference between product A and product B?
The placement of the oxygen.
Placement of the oxygen is one difference. What else? Placement of the pi bond. What's higher in energy, the sigma bond or the pi bond? The pi bond. Okay, so if I'm going to look at product A versus product B, what's going to be probably the most important factor for me to consider?
Where the pi bond is.
Where's the pi bond located? Okay, so where's the pi bond located, or how is it located differently in product A versus product B?
Does that have to do with it being on top or underneath, or is it like what carbon is attached to it?
The on top or underneath is just an artifact of how the drawing software sets that up. Here's a hint.
Oh, it's the. Because it's closer to the substituent.
It's not that it's closer to the substituent. You're right path, potentially just wrong words. Right idea, wrong language, but yes. Okay? It's the substitution pattern on our pi bond. Okay? A tri-substituted pi bond is more stable than a di-substituted pi bond. Okay? So in this particular scenario, we're saying product A is preferred. Why is product A preferred? It's a more stable double bond.
Because
That's
of
why.
the placement of the pi bond.
Yep. Okay. Could we create a system where product B is favored? Yeah. Okay. But that's a different question, and actually a question technically isn't harder, it's just different. We actually answered that by looking at the carbocations. You create a system where the carbocation is the primary driver of the reaction as opposed to the alkene. That requires digging into much more chemistry in the relative energy of all of those systems. So that's looking at really hardcore energy diagrams, which is something that shows up in a little bit in OChem 1 and mostly in OChem 2. Okay? All I'm trying to get you to do is to recognize that primary pattern behind it. So,
And for a product, because obviously they're both products you can get, it doesn't change the reaction type though, does it?
nope,
still
it's
gonna
the
be-
exact same reaction type. It is still a substitution. It just happens that in one case you did a substitution followed by, it's weird to say followed by resonance. Resonance is always there, but
You like acted on the resonance.
you acting on different forms of the resonance structures.
Within the reaction.
Yep. So it looks like something different has happened. It's still a substitution reaction. And yeah, until we talked through it, I couldn't figure out why I took off points. And
Well, cause I didn't,
That
I just said
pushed.
pi bond
Yeah.
and explained
so
what
you
happened.
addressed a good how.
Yeah,
Ideally, there would have been a little bit more, but I did say curved arrow mechanism or words. So the words I was looking for was resonance. Yes, resonance was good enough. I can accept that. But now, why should product A be the preferred? That was the point. Other questions? According to my clock, we got 3 minutes. Admittedly, my clock has been very weird as of late. I think we've already done question 1. We already do question 1? Does that look familiar to y'all?
yeah, oh, never mind, sorry.
I know it's familiar to you, Annie. That's not fair. I'm not asking you because I know you've done it. How does the rest of the class feel? Have we done that one? Does it feel familiar at all? Question 1? Going once, twice, 3 times, 2 minutes. Okay, we'll look at that one. Okay, so in this case, this would be a good case if you had multiple colors or a highlighter to actually use it, and in particular, tackle that unlikely word. That unlikely word is kind of an important word because it's going to change your interpretation of this. Okay, and then it goes through and says nucleophilic addition reaction. Okay, same process as before. We should be able to go through and answer the question before looking at the answers. Okay, so I want a nucleophilic addition reaction. Okay, reaction. Have to have an arrow. What is the nucleophilic addition going to give me information about? It's going to sound rude. Stay out of it. So we would need a nucleophile to donate electrons. What is it donating electrons to? So what you just addressed was the nucleophile term. I agree. What is an addition reaction? Break a pi bond, which means we had to start with a pi bond and we would end with not a pi bond, okay? Theoretically with the nucleophile now connected to it. So the nucleophile is somehow donating electrons to one of those atoms. I'm going to change the location of where I put the nucleophile. Which is what then causes the pi bond to go through and break and move up. Okay? Those are our basic pieces. How many different pi bonds have we seen? So if we had our functional groups all memorized, we could go through and list out a whole bunch of functional groups like alkenes, alkynes, ketones, aldehydes, carboxylic acids. Okay? So do we have lots of pi bonds? Yeah, there's tons of pi bonds. Are all of those pi bonds the same? No. Right? How are they different? Drop in a hint. Okay, what they're connected to. Okay, can you elaborate more on that? These would be polar pi bonds. These would be non-polar pi bonds because of what that carbon is connected to. Okay? So we could go through and say, because the pi bond that we drew within our example of this reaction, we didn't actually specify what the atoms were. Okay, which I know you'd be like, well, they're implied. Yeah, so we could put in question marks. But now the question becomes, is what are those question marks? More than likely, one of them is going to have to be a carbon. We don't really get much of a choice on that because it is organic chemistry. Okay? But now what's the identity of that other question mark? Okay? Is it a carbon? Would that make sense? I'd be putting in the product a negative charge on a carbon. Do I like that? No? Why not?
Carbon doesn't like to be negative.
Carbon doesn't like to be negative. Okay. So what if I made it an oxygen? I'm still putting a negative charge, but now I'm putting that negative charge on
Oxygen.
oxygen. Is oxygen okay with a negative charge?
It can hold it.
It can hold it. So if we look at these two options, which one do you think is more likely to represent the nucleophile addition reaction? Where we have it as an oxygen or where we have it as a carbon? Oxygen. Oxygen belonged to our class of polar pi bonds. So if I want to do a nucleophile addition reaction, I want polar pi bonds. That makes sense. Okay? But remember, it says unlikely, so my answer is probably going to be
Not that one.
the not polar pi bonds, right? Or our non-polar pi bonds. Now we could spend the time to go through and look at our answer choices. And I think I need to erase a little more. Yeah. Oop, and maybe a little more there. Okay, maybe I should be better about erasing things. Okay, and now we could go through and look at each of those. Okay, well, the first two answers immediately show us oxygens. And what did we just say? That's polar. Those are good options. I don't want those options because those are good, and I want the bad ones. So A and B are wrong. C, ooh, that's a nitrogen, not an oxygen. Well, what do I know about nitrogen? Is it electronegative?
More than carbon, but
Yeah.
not.
More than carbon, less than oxygen. How electronegative is it? Okay, there's a force, a strong force called hydrogen bonding. It's a strong force because it involves very polar bonds. It's what we talked about when we talked about intermolecular forces. Okay, very polar bonds involving what elements? For hydrogen bonding. So hydrogen is one of them. F, O, and N. F, O, and N are the three most electronegative elements, which means when I pair any of those elements with hydrogen, I have a wicked difference in electronegativity. So different that I might call that bond polar. So if I see oxygen, nitrogen, or fluorine connected to anything that's not oxygen, nitrogen, or fluorine, that bond is polar. Okay? Which means C doesn't work. How about D? What's in D?
Oh, it doesn't. Oh,
D is carbon and carbon.
non-polar.
That is the epitome of a non-polar pi bond. That looks very unlikely. If I move to E, what do I see? I see the nitrogen again. Nitrogen, very polar. And one of the things that I would hope you would note is that we keep constantly referring back to older content. That older content holds clues that allow us to navigate forward. Or we have to memorize everything from the beginning, and that becomes a problem. What we're trying to do is build content so that we don't have to memorize as much. We apply the old content. That sets us up with the answer where D is the most unlikely to undergo a nucleophilic addition reaction. Kind of, sort of? So there's a reason we've been defining language. There's a reason we've been defining electronegativities and properties of atoms, because you can now manipulate those things to get you answers without having to memorize the world of chemistry. With that, we're done.